Alright, so we've missed a few days, and I want to make sure that we're on for this, so I'm going to do a couple examples for you guys. I won't be doing this for everything, but if we get a little too far behind, I'll go over these. Now, this past portfolio dealt with some of these, and indeed these are exact problems from the portfolio that I just changed some numbers on. There's really only two different kinds that I gave, by and large. And they look like this. It's integrate the function using u-Substitution, then integrate it over the interval given using the FTC2 if possible. That is, using the evaluation theorem. Now, the directions in your portfolio were a little more robust than this, but here's the function. It's 2x squared over 5 times the quantity, 3x cubed plus 1, all cubed. And then the interval for the second part of this problem is 0 to 2. And I want to show you how to go about doing this, and this is one of the type of problems where there's division. And I want you to note that I could have just as easily written this as the square root of 3x cubed plus 1 instead of cubing the whole thing, and it's exactly the same kind of problem, except there's a square root in it, and that handles the third type. So with a couple exceptions, there are no other problem types than just these. So I'm just going to scroll down here, and let's look at this for a second. So we want to look at this, and in order to be able to use u-Substitution, remember, the whole point is you need to find a function that is plugged into another function such that the function that is plugged in has its derivative sitting somewhere else in the problem up to a constant. So here's what I look at. I say, okay, well, here's a cubic, and inside of this cubic, we've got our boy, 3x cubed plus 1. So if I come over here and I think, okay, I'm going to take the derivative with respect to x of 3x cubed plus 1, and I do this in my head, of course. If you take the derivative of this, well, the derivative of that constant dies in a fire. You bring down the 3, you get 3 times 3 is 9x squared. Now, right here, I have 2x squared. So up to a constant, it's exactly the same. That is, the x squared is there and here. Now, the only thing that's different is the 9 and the 2, but that doesn't matter. We can fiddle around with constants and figure that out just fine. Technically, it's not just a 2, it's a 2/5. We'll deal with that in a second. But I know that this is ripe for u-Substitution. So I'm going to go ahead and write the problem again, and we'll do it in a triggering con yellow here. So I'm going to say the integral of, and then look, you've got this 2/5. The very first thing I'm going to do after stating the problem is just pull the 2/5 out. So I don't have to deal with it. I'm just going to pull the 2/5 out and not worry about it anymore. So what's left? Well, x squared on top, and then on the bottom is 3x cubed plus 1 all cubed. Now, this could have been the square root of 3x cubed plus 1, and this would still work out. The 3x cubed plus 1 is the thing that you take the derivative of to get the x squared, again, up to a constant. And it doesn't matter what it's plugged into. So long as you can actually integrate it after the u-Substitution, you're fine. Don't forget your dx at the end. This is literally the times the tiny change in x. So let's look at this. When we do this integration, we need to know our u and our du. Now, I come down here when I have a pen and I do let u equal whatever and so forth. You don't have to do this when you're typesetting it in LaTeX. Just write out a paragraph. Say, at this point, we will choose u to be this. Taking the derivative gives us this, and then we can plug in using the following, and then just give the next step. That's fine. Just do it in a paragraph, and tell me what you're doing with words. But when you're doing it on paper, you have the advantage of being able to see this. So let u be the thing that you want to take the derivative of. 3x cubed plus 1, the whole thing. 3x cubed plus 1, okay? Therefore, we say du, and again, don't trouble yourself trying to find the therefore and all that in LaTeX. Don't worry about it. Instead, just write all this up in words in a paragraph and tell me what it looks like. Du is, well, the derivative of this, we did the derivative up here, it's just 9x squared dx. Remember, du dx is what we found. This right up here was, if this was the function u, we actually literally found du dx right here. I just multiplied both sides by dx, because it's just a tiny change in x to get this. But we don't have 9x squared up here, we have 2x squared. And what I want... don't look back at the problem. What we have up here is x squared, and what I have is 9x squared, which is the awesome thing about pulling out the 2/5. So remember, this is the problem you're working with, not this. So x squared is what we want. We have 9x squared. Just divide both sides of this by 9, or multiply both sides by 1/9. Therefore, 1/9 du equals x squared dx, and that is all of our work that we need. So now we can write this as, don't forget the 2/5 times the integral of, and then we remember everything. What was x squared dx? Let me put it in this really ugly green here. X squared dx. Look, right here. X squared dx. X squared dx is 1/9 du. So instead of x squared dx, I'm going to write 1/9 du. So I'm literally going to write 1/9, like this, 1/9, and then du. We usually want to be over here. Cool. Over, and then it was something cubed. Well, it was something cubed, and then what was 3x squared plus 1? Look here. What was 3x squared plus 1? Look down here. 3x squared plus 1 was just u. So that's just u. And that's where everything went to. The 2/5 was factored outside first thing so that we didn't have to deal with it and all this garbage down here. So that's what you're dealing with. So you're taking all of this. Well, we're just going to go on to the next step now, which I would say pretty easily is just pull out the 1/9. Just pull out the 1/9. So if you pull out the 1/9, on the top, what's left is 1 over u cubed du. That's the entire antiderivative or integral, which we're doing. And if you pull out the 1/9, well, you're just going to multiply 2/5 times 1/9. I'll do the math for you here. 2/5 times 1/9, like this. And you all can do this math. So I'm going to come back down here and do that math for you. 2 times 1 is 2, obviously. And 9 times 5 is 45. So 2/45 times the integral of, and you don't know the integral of this, but 1 over u cubed is just u to the -3rd, du. And now we're just going to do the math. So it's 2 over 45 times, and then we're going to do the math here. So this is you're going to increase this by 1 and then divide by that new power. So you're going to take the u to the -3, you're going to increase it by 1, and then you're going to divide by that new power, just like this. Okay? And then it'll be plus c, as always. So I'm going to come back down here. We're just going to come right back down here, like this. So this will be 2/45 times negative, because -3 plus 1 is -2. This will be -1/2 u to the -2 plus c. And then all we have to do is just distribute back through our 2/45. So this will be -1 times 2 is -2 over 45 times 2 is 90. Or you can just notice that there's a 2 on top and a 2 on the bottom, which is what I'm going to do, and save yourself a step. So there's a 2 on top, 2 on the bottom. So this is -1 over 45 times u to the -2nd. Or if you prefer, instead of writing u to the -2nd, write 1 over u squared plus c. I'm just going to scroll down here. And we're going to finish this problem up. We'll come all the way back over here and finish this up. So this is -1 times 1 is -1 over 45 u squared, 45 u squared plus c. And that equals, well, what was u? Well, u is just 3x cubed plus 1. So this will be -1 over 45 times, and then instead of writing u, write what u was, 3x squared plus 1. 3x squared plus 1. And remember, u was squared, so this is still squared plus c. And that's your answer. That is the integral. And that's all that there is to it. So the other thing that you have to look at is now we want to integrate over 0 to 2. And notice that this thing says do it using FTC2 if possible. So we need to check to make sure that this actually works. And here's how you do it. Is this function f of x continuous? Is this function f of x continuous on this domain? So is there any number in this 0 to 2 that you can plug in such that, I guess the only problem we have here is we divide by 0. Is there any number between 0 and 2 that we can plug into this that we divide by 0 or that we have a negative under a square root? Ask yourself that question. Or we have a 0 or less number inside of a natural logarithm. Well, no. We're adding 1 to this number, and the numbers are all positive. Well, they're all non-negative. 0 is included too. So the smallest that we can get this thing is plugging in 0, and we'll get 5 on the bottom. 0 cubed is 0 times 3 is 0. Plus 1 is 1. 1 cubed is 1 times 5 is 5. That's the smallest we can get the bottom. We cannot get the bottom to equal 0, though. There's nothing that we can plug in here from this domain to get 0 out, so FTC2 is going to work. However, if there was a number in this interval that we could plug in for x, and it breaks it, then we're no longer good. So if you go back to math analysis, and you look through how to check for negatives under square roots in rational functions, you'll figure out what it is that we're doing. That's 3.7 from your math analysis notes if you want to go back and look over that. But just check everything in this domain to see if there's anything that is dividing by 0, so set the denominator equal to 0 and solve. And then if you have any negatives under square roots. If you have a division by 0 or a negative under a square root in the interval that I gave you, it's not possible. And it's not possible because it's not continuous on the interval I gave you. That is the reason you give me. Otherwise, you're good to go. It doesn't matter whether or not it works. You need to tell me that it works. If it works, it means that it was continuous over the domain. That is, there was nothing that broke it. If it doesn't work, it means it was discontinuous on the domain. You tell me that, and then you're done. But this does work, so we're going to do the integral from 0 to 2 using the FTC part 2. So here's that. We're going to do the integral from 0 to 2 of this entire function. And let's try and remember it here. It is 2x squared over 5 times 3x cubed plus 1 cubed. So it's 2x squared over 5 times 3x cubed plus 1 cubed dx is the integral that we were doing. I'm pretty sure. 5 3x cubed plus 1 cubed, 5 2x squared. Yeah, that's exactly the right thing. The good thing is we know the integral now. This is, by the FTC part 2, just this guy right here, evaluated between 0 and 2. So I'm just going to write that out. The integral of this, we've already done all the math, so the integral of this is just negative 1 over 45 times 3x squared plus 1 squared, evaluated from 0 to 2. That's the whole thing. Don't worry about the plus c. Remember, the FTC is going to take care of that. So, all that we have left is just to finish the problem off. This is, by definition, just this entire thing here with a 2 plugged in. So at the top, so let's write that. It's negative 1 over 45 times 3 times 2 squared plus 1 over 2. That's the first thing. Minus this thing right here, the integral, with 0 plugged in. That's always how it works. Just look back in your notes. So it'll be minus the exact same thing, except instead of plugging in 2, you plug in 0. 45 times 3 times 0 squared plus 1 squared. Now I hear some of you asking the question right now, why aren't we plugging these two bounds into this? Because this was the integrand. This was the thing that we were trying to take the integral of. Once you've done the math, that is the first part of the problem, this is what you get out. This is what you plug it into. If you look back, this guy right here is your capital F in your definition that you evaluated it. This guy right here is your little f. There's a big difference. This guy is the antiderivative or the integral. This guy is the integrand, the original function that you start with. If you take the derivative of this, you get this. That's FTC part 1 is what it says. Let me get rid of all this stuff. Cool. Now, let's continue. So, we just do the math with all of this. So I'll come down here and I'll finish this math up. So this is just, on the top, -1 over 45 times, and I'll try to do a few steps at a time. Let's see here. 2 squared, I'm up here. 2 squared is 4. 4 times 3 is 12. 12 plus 1 is 13. So that's 45 times 13 squared on the top. Minus, and then this is even easier, -1 over 3 times 0 squared is 0. 1 squared is 1. This is just minus -1 over 45. So I just simplified this down. And you can do it in a paragraph format if you want to. You can do it step by step and show me every single thing. I don't care, whatever you want to do. But the only step left to finish this up is just say, well, this is just -1 over whatever 45 times 169 is. Okay, minus a negative is plus a positive, plus 1/45. So if you do the math on this and reduce it down, it'll turn out to be 56 over 25/35. That's fine. That's awesome. That's an answer. That's it. That's the area. That's as reduced as we get it. That's the whole problem. You're done. Let's scroll down and do another one. So this is the other kind. This is where your function is plugged inside of some sort of other elementary function that's a bit more complicated than a square root or a cubic or whatever. And this is over the bounds -1 to 1. Cool. Let's take the integral of this. So we're going to go ahead. First step, we're just going to pull out the 2/3. Do the integral of t squared cosine of t cubed plus 3. I will take off 5 to 10 points if I see anyone do this. If you write this, dx. No. Your variable is t. Do not write x here. This would be dt. And write dt the entire time. Please be careful with that. That is your variable. So, this is, again, a u-substitution. So we better be able to find a function, in this case, t cubed plus 3, take the whole thing, such that its derivative is sitting somewhere else in the problem, up to a constant. So the derivative of t cubed plus 3 is 3x squared, and we're close. We've got a t squared here, and this original function has to be plugged inside of another function that we can actually take the integral of. Well, we can integrate cosine. We know what that is. So we're good to go on u-substitution. So let's look at this. So we're just going to let our u be the thing that was plugged in, this guy right here, t cubed plus 3. Why do we have to take the plus 3, you might ask? Try it without it. If you don't take the plus 3, when you plug back in your u, you're going to have the cosine of u plus 3. We don't know how to integrate that right now. So that's going to be the problem that you run into. But if you take the whole thing, the derivative will take care of that plus 3 for you. Look at this. We say, therefore, du equals, take the derivative of this. The 3 dies in a fire. You get 3t squared. That's the power rule. Okay, but remember, in our problem, not our problem up here, but our problem right here, we don't have a 3t squared. We have a t squared. So we just want a t squared. We've got a 3t squared. So I just say, and 1/3 du equals t squared. Again, dx, no, t, dt, like that. Okay, so keep in mind, we're working with dt's. Second, how did I get from this step to this step? I just multiplied each side by 1/3. Why did I do that? Because what I've got up here is not a 1/3, is not a 3t squared. If there were a 3 sitting right here in the original problem, then I would not have to do this step. But I have to do this step because there isn't a 3 sitting up there. It's not that nice. But we can continue from here. This is very easy. This is, do not forget your 2/3. It's another problem I see all the time. This is the integral of, and now we're just going to do our substitutions. So, look here. Our t squared dt is right here. And look here. Our t squared dt, it's separated a little oddly. I'll give you that. but there's the box. Our t squared dt is here. We could have just as easily rewritten this as cosine t cubed plus 3 times t squared dt if you wanted these things straight next to each other. But the t squared and the dt both become whatever's on the other side. So they both become 1/3 du. We're still using u's. Even though we use t's here, we still use u's. What's left? Well, the only thing that's left is the cosine of whatever t cubed plus 3 is. So it's the cosine of whatever t cubed plus 3 was. And what was t cubed plus 3? Look right here. That L just means let. What was t cubed plus 3? It just means u. T cubed plus 3, so instead of writing this t cubed plus 3, we just write u. And now I'm just going to write it all in one color. I'm going to pull out the 1/3 and multiply them. 2/3 times 1/3 is 2/9. And keep pulling out your constants as often as you can. Make this as easy as possible. Times the cosine of u du. That's the whole problem. So now, all you have to do is look in your notes and tell me, what is the integral of cosine? Because we can do it now. So this equals 2/9 times, and then in brackets, whatever the integral of cosine of u du is. So if you take a moment, it is sine of whatever variable, u, plus c. And then the only thing you have to do to finish is remember that this u needs to be subbed back in for whatever u was. This guy right here, t cubed plus 3. So your final answer is going to be 2/9 the sine of, and instead of writing u, we write back what u was, now that we're done with the u substitution part. T cubed plus 3. How do you know when you're done with the u substitution? Once you've done the integration. U substitution is a technique that helps you integrate functions. Once you've already done the integration, that is, you're not writing the integral symbol anymore, this step to this step, you don't have to keep the u's. Put your u's back. Okay? So there we go. That's the answer. That's the whole thing. 2/9 sine t cubed plus 3 plus some constant c. If you take the integral of this by the fundamental theorem of calculus part 1, you should get t squared cosine t cubed plus 3 times your 2/3. And that's exactly what you'll get. Check it if you want to. Now, over the interval from -1 to 1, this is going to give a very weird answer, and that's fine. We're just going to leave it as a very weird answer, but we can also approximate it, because I believe that the problem wanted us to approximate it. So we're going to do the integral. The second part of this is checking it. So we're going to do the integral from -1 to 1 of 2/3 t squared cosine t cubed plus 3 dt. So the first thing we need to do is check to make sure that this function is continuous over this interval. Well, cosine is continuous everywhere. T cubed is continuous everywhere. A linear function plus 3 is continuous everywhere. T squared is continuous everywhere. And multiplying something by t cubed is continuous everywhere. So we just did a bunch of stuff with continuous functions. Yeah, it's continuous. You can check, though, but there's no way for us to divide by 0, have a negative under a square root, or a fourth root, or a sixth root, any even root, and there's no way for us to have a non-positive number, that is 0 or a negative number, inside of a natural logarithm or any other kind of logarithm, because there are no logarithms. There's no logarithms, no square roots, no divisions. We're good. No divisions by variables, at least. I guess there is a division by 3. But on that interval, we're good. We're actually good on any interval. But if you don't believe me, go look between -1 and 1 on Desmos. You might have to use x's instead of t's to get it to look. There's no breaks in the graph. You can see that very clearly. There's nothing that we can plug into this that's going to jack it up. So we're good to go. If we weren't good to go, we would just say that this does not work because it's discontinuous on the interval and we're done. That's it. FTC Part 2 requires the function to be continuous on the interval that you're integrating over, including at the bounds. That's why it's closed. But we can do it. So this just equals, what's just going to equal this minus the plus c part evaluated between 1 and -1. So this is just going to be 2/9 times the sine of t cubed plus 3 evaluated between, and sometimes you'll see books do this, and you're welcome to do this. Keep track of the bounds like this, between t equals -1 and t equals +1. Sometimes we have to do this to keep track of it. Right now there's only one variable. Sometimes there's more than one variable flying around. So you notate it however you want to. We leave the plus c part off because we don't need it. We're just going to subtract. This guy evaluated. Let me do this like this. Let me do this t equals -1, 2, and then I'll do it up here like this. T equals +1, so that I have the different colors in here. But we're just going to do it between the red and the orange guys here. So look here. This is just going to be 2/9 times the sine of something cubed plus 3 minus, this is literally what this notation means, 2/9 the sine of something cubed plus 3. Okay? That's all that this means. It just means copy this thing twice, subtract the second one from the first one, and then do the first one at the top bound, like this. Do the second one at the bottom bound, like this. That's literally all that that notation means. Do not get hung up on that. From here, it's as simple as just doing a little bit of math. And good news is we don't have to do a lot of math. So this is just 2/9 times the sine of, well, 1 cubed plus 3 is 4, minus 2/9 times the sine of, -1 cubed is -1 plus 3 is 2. So if you just want an exact answer, that's it. That's the exact answer. If you want to be really fancy, I guess you can factor out that. Do you know what the sine of 4 is? Not 4 pi, just 4. Do you know what the sine of 2 is? Yeah, me neither. However, Desmos does. Wolfram Alpha does. Your calculator does. Make sure that it's in radians. And you'll get that this is just 2/9 times the sine of 4 minus the sine of 2. Hey, just shove it into Wolfram Alpha. And you'll get that it's -0.37. It's about -0.37. So if I'm going to say that something is about something, I'm going to say that it's about -0.37. The actual number is -0.37024442714. It goes on forever. It's transcendental. However, this is to the 100th place. The thing after the 7 was a 0. So that's it. That's your answer. There's negative area. When I say signed area, I just mean you can get negative area. All that means is that on that interval between -1 and 1, the function has more area under the x-axis than it does above the x-axis. That's all that I mean by signed area. And that's it. It's a very weird-looking answer, but it's totally the answer. And I want to give you all just a little bit more practice with this notation here. I just want to give you one little quick example right here underneath the problem. This won't even take but a second. Watch this. If I want to say, remember that it works like this. F of x evaluated between x equals a and x equals b. First off, this notation is just a more compact way of just writing it like this. It's the exact same thing. And this is just f evaluated at b minus f evaluated at a. And sometimes we don't write the x equals part. We just write b and a there. So if I were to say, for instance, the square root of x evaluated between 4 and 9, that would just be take literally everything here and write it, and then evaluate it at the upper bound, and then subtract. Always subtract. Take another copy, so square root of something, and then evaluate it at the lower bound. So in this case, this is just 1. That's all that notation means. Do not get hung up on that. So that's why we copied and pasted this. So when we evaluated 2/9 sine t cubed plus 3 between these two bounds, it looks like 2/9 sine of something cubed plus 3. That's why I wrote 2/9 sine of something cubed plus 3, 2/9 sine of something cubed plus 3, and then I evaluated at its bounds 1 and -1, 1 and -1. I hope this helps. I'll see you all in class the next time I see you.